Okay, welcome everyone to my continuation of my lecture, Quantum Topology without Topology. And well, today we certainly won't see any topology at all. We are still doing parts of algebra. And today I really would like to discuss something I really like. Strictly speaking, it's not necessary for the goal we have in mind to construct as many quantum invariants as possible, so those functors from those nice diagram categories to some algebraic categories. But today I basically want to discuss a very natural question, like, remember those quantum invariants were those functors, as I said, to some nice target categories. And in some sense, you would like to ask the question, like, can you classify those quantum invariants? That's a really hard question. Maybe you should start with something like, can you classify the possible targets? So I would like to talk a little bit about classifications of those possible target categories. And last time we have seen that these are basically those things, those enriched categories, Fiat, tensor, or fusion. So basically pivotal, linear, and then you have to decide a little bit whether you want to be abelian or additive. So whether I want to lay the focus on simple objects or on decomposable objects. Kind of the analog question you should have in mind is, well, if you see finite groups for the first time, then, well, you would like to ask, can you classify finite groups for a certain numerical invariant, right? Fixing some verticals, fixing some numerical invariant, like the size of the group. Can you classify all groups of order 515? Usually those questions are hard, but you can say something like a classical statement, probably all of you have seen at one point, is like all finite groups of prime order are cyclic. And this is a classification which is pretty easy to do, to prove. And maybe there's some analog for those categories turning up in quantum invariants, and that's what I'd like to discuss today. So the answer will be, in some sense, so the question is, can we, as I said, can we hope to classify these things? And the answer is, well, yeah, maybe. as usual in life, the answer is maybe. This lecture will be a bit long, so I will split it into part A and part B, and the classification will mostly be in part B. Because it's just much easier to try those classification for the semi-simple case. Because the semi-simple case is just much easier than the non-semi-simple case. And in the first part, I will basically discuss some very nice algebra, actually. So just stay with me. It will take a while to get us there, but it will be worthwhile. I really like it. As I said, strictly speaking, it's not necessary for our final goal. So if you are not like me and you're not like, oh yeah, a fanboy of algebra anyway, of any kind of categorical algebra, then you might want to skip lecture 8. If not, then there will be, I promise, there will be a lot of really, really nice ideas. In particular, one of my favorite theorems ever, the Perron-Fabini theorem. This is really good. This is a really workhorse, and if you've never seen it, it's worthwhile to learn it. Anyway, what we will see a lot here is, well, our graphs. So here's a graph. It has two vertices. I call them V1 and V2. It has, what is it, 3 arrows. Here you go, something like this. And an arrow here. And a graph for me is basically something like this, an oriented graph, vertices, edges. And I also usually put labels on the edges. So if I don't have any label, then the label is 1. Okay, so this graph here would secretly have a 1 here. So 1, a 2, and a 3. And this is just my shorthand notation for, let's say, secretly here would be whatever, 2 parallel edges, which I usually don't like to draw. Instead, I identify this just with 1 edge of label 2, right? And such a graph, so those graphs will play an important role, which is a bit funny because, well, we'll see. It's very surprising. It's a beautiful and very surprising idea why these graphs show up all the time. But anyway, these graphs correspond to integral matrices in the following way. So the vertices correspond to the rows and columns of your matrix. So it's a square matrix. Vertex 1, vertex 2, and you just put in the numbers you see on the edges. So on the diagonal, you see all the loops. So here's the non-existing vertex from V1 to V1, so you put a 0. Here are the 3 parallel vertices, so 3 parallel loops here from V2 to itself. So this is V1, this is V2. Yeah, and then whatever. The vertex from V1 to V2, as the edge from V1 to V2, and the edge from V2 to V1. Oh, the 2 edges from V2 to V1. And the whole point is, just to let me make this clear, that graphs and those matrices with natural numbers as entries are their one-to-one correspondence. So you can either think of a graph or, so this wasn't a graph. You can think of a graph or of a matrix. Right? So integral matrices are graphs. Graphs are integral matrices. They go hand in hand. And I will use this, basically, I will use this, so I to use the symbol gamma for either a graph or integral matrix. As I just said, they're the same anyway. So, okay, this is worthwhile to be repeated because a lot of people don't know it. And it's a really, really, really beautiful idea. So graph theory, in some sense, is only doing, well, studying integral matrices. And studying integral matrices is just doing graph theory. Because every integral matrix is a graph, and every graph is an integral matrix. And all notions you can think of for graphs, like isomorphism of graphs, on the side of matrices, this would be a permutation of permutation-based change of the matrix. So this is really, really a nice one-to-one correspondence. Obviously well known for ages, and the main point is that this will be of importance in our study of, well, quantum invariants. And that's a bit surprising, we'll see it. It's very beautiful, stay with me. Anyway, yeah, so just to remind you of my convention, so X usually is a general object, L will be simple objects, remember the object without substructure, and there will be P's usually. Usually I mean by P a projective or projective indecomposable object. Then there's an I, the dual, the injective or injective indecomposable object, and there's a Z, which is just an indecomposable object. Remember that there was this huge difference, which I'm going to explain in a very nice example today, between L and Z. So whether you focus on simple objects, whether you have something abelian, or whether you focus on indecomposable objects, whenever you have something additive. Right? Remember, elements of a theory, periodic table, you want to write it down, and it depends a bit what are your elements, things without substructures, the simples, or things that you can't decompose further, the indecomposables. And also important to recall is that in this one case, semi-simplicity, all of these agree anyway, and you don't have to care anymore. There's no difference between simple and indecomposable, whatever. So semi-simple just makes your life much, much easier. Sadly, remember also from last time, or maybe, yeah, or actually the sixth lecture, that semi-simple is really, really rare. It basically only happens if you have some copies of vector spaces. So life is sadly not semi-simple, and well, you see this in chemistry, right? In chemistry, it's actually pretty complicated. Things tend to form very strange bonds, and in the semi-simple case, basically, you could think of everything falls apart into its elements by default. It just falls apart, and it's just not going to happen, right? Things form bonds, and this is important, right? Life would be pretty boring if everything would be just an element. It just falls apart, and it's just an element. Anyway, I started waffling, so let's start with a really, really nice example. the representations of groups, representation theory of groups, and secretly of Hopf algebras as well. And the point was that in those cases, you get those tensor categories, those Fiat categories. We will see. So let's say you have a finite group. So G is my finite group. It has some order M, doesn't matter so much. And there is some underlying field K. Let's say it's algebraically closed, whatever. You certainly have this Hopf algebra structure, multiplication, unit, co-multiplication, co-unit, and this funny antipode. And all this is saying is that you can tensor representations and you have duals of representations. And in coordinates, those maps are actually not very hard to write down. So multiplication and unit are the ones from the group anyway. So group multiplication and the unit in the group. And here are the other ones. So co-multiplication is just this diagonal thing. Co-unit just turns everything to one, and the antipode is just inversion. So it's kind of the baby example of Hopf algebra. All of the structures you're looking for are actually already present in the group anyway, or are completely boring, like the co-multiplication. Right, so you have to find a map. So co-multiplication, remember, it was you have to find a map from one input to two inputs. And the stupidest thing you can do is just to take your input and just copy it to everywhere. And this is exactly this map here. So kind of the most boring thing you can imagine. And that's it. That's what you, well, that's the Hopf algebra structure on a group. So group is usually the easiest example, as I said. And this just means that, well, let's say finite dimensional modules over my group is k-linear, abelian, rigid. Actually, it's pivotal, but it doesn't matter so much. K-linear is clear by definition. Abelian is also clear because you take all modules, and rigid means monoidal with duality follows from, oh, no, not abelian. Rigid follows from the existence of those two guys here, basically. So antipode gives a dual, and co-multiplication gives a tensor product. And the funny thing you see is an inequality, and a very important one, a beautiful one, and a very, very important one. It's super. It's really nice. It's here 8.1. Okay, it's really nice. So 8.1 is the following equality. So let's say, okay, in this case, you have a finite number of simple modules, Li. Okay, and let's say you know the dimension of those guys. And then you take the square of them. It's a little bit funny that you take the square, but believe me, you should take the square of the dimensions, sum over all of them. And on the other side, you have the dimension of the group, which is just the size. Then you will see that here this is always lower or equal. So the squares of the dimensions of the symbols is always lower or equal than the size of the group, or the dimension of the group ring, which is, by the way, the same for any finite dimensional algebra. So you always have this really nice one. The square of the dimensions of the simple modules is always lower or equal to the dimension of the algebra. Okay, so what is a real equality is the dimension of the algebra would be dimension of L1. That's why it's a square here. Dimension of Li times dimension of its projective cover. The projective cover is usually much bigger. It's always bigger than the Li itself. It could be equal, but it's always bigger at least. So you get this inequality. And the point is that equality happens in both cases. So it doesn't matter. If and only if things are semi-simple. So equality holds if and only if you're in a semi-simple case, which is the case when those two are the same. And that's why you get the square here, right? So if those two are the same, you get exactly the square. And for group rings, there's an even more explicit condition, which is called Muscular's theorem. So for group rings, this happens if and only if P, the characteristic of your field, doesn't divide the order of the group. So, for example, if the characteristic of your field is 0, you like complex numbers or whatever, then it's always linear simple. It's a really, really beautiful result. But you have this inequality, which always holds, and it gives you a method to check whether something is semi-simple, or if you know that you're semi-simple, it gives you a method to check whether you've found all simple modules, because you always want this equality to hold. Okay, and I give you now an explicit example. How this inequality is basically a measure for non-semi-simplicity. Okay, and it's a really, really easy example and beautiful. So it's easy because the only thing I consider is this polynomial, basically, and everything follows from this polynomial. It's x minus 1 to the fifth, and you could do x minus 1 to the third or whatever. You will see it. I just decided to go to characteristic 5. Anyway, so x minus 1 to the fifth. I hope you won't be surprised if I expand it and you see the binomial coefficients turning up here. So 5, 10, 10, 5, and so on. Anyway, in characteristic 5, this dies, this dies, this dies, this dies, of course, and it's just x minus 1. X to 5, x to the fifth minus 1. So x minus 1 to the fifth in brackets in characteristic 5 is just x to the fifth minus 1. I should have used cubes. Anyway, so this has actually a name. It's called freshman's dream, because it's just this wrong equality, right? X minus something minus 1 to the p is always x to the p minus 1 in characteristic p, and this is obviously false. Let's say for the complex numbers, right? That you get binomials, but it's kind of the naivest thing you can imagine, and that's why it's called freshman's dream. Anyway, so freshman's dream, and what does freshman's dream actually tell you? Freshman's dream tells you that this is obviously a decomposition into linear factors, just 5 of them, and all of them are the same. Is a decomposition of this part, which just means you only have one fifth root of unity, because the solutions of this equation here are the primitive fifth root of unities, right? Or the fifth root of unities. But because it's equal to the other side, there's only one, and that's 1. Okay, so in characteristic 5, there's only one fifth root of unity, and that's 1. In all other cases, you're happy, but in characteristic 5, you only have the fifth root of unity. You have other roots of unities. For example, over C, the other example, you could take something like, now I need to draw them, those exps, and you all know how it looks like. It's a pentagon. Oh, this actually isn't such a bad pentagon. So pentagons are, by the way, really hard to draw. So here's one. This is a complex plane. And these are the fifth primitive root of unities, and the coordinate expression is this x here. It doesn't really matter. You have 5 of them, as you can see. It's the edges of a pentagon. Okay. So what you do is you now consider this matrix here, which, as you can see, is just the action of the generator 1 on Z mod 5. Right? It's just shifting everything by 1. It sends 0 to 1. It sends 1 to 0. It sends 2 to... it sends 0 to 1. It sends 1 to 2. It sends 2 to 3. It sends 3 to 4. And it sends 4 to 5. 4 to 5, but 5 is 0, so it sends 4 to 0. So just this cyclic thing, right? It's this graph, the cyclic graph with 5 vertices. You just go around. Yeah, this is a really bad cyclic graph with 5 vertices, but yeah. Let me try again. 1, 2, 3, 4, 5, and you go around. Right. And what this equation upstairs here tells you that, well, except in characteristic 5, let's say over the complex numbers, you the drawdown form of this matrix is actually just a diagonal matrix with the fifth root of with the 5/5 root of unities on the diagonal. But in characteristic 5, there is only one. So the only eigenvalue of this matrix is 1, and it's just a big drawdown block. Okay, and this tells you, well, this is basically the regular representation. So this one of the group ring. So in characteristic 0, it just decomposes into 5 simple one-dimensional modules, and in characteristic 5, it's just what it is. It's indecomposable. And if you go on, then you will see the following. So if you're happy and you're not of characteristic 5, then you can write down, let's say this is examples over the complex numbers. Let's say over the complex numbers, you can write down the simple modules. They are all one-dimensional, and they're given by specifying one of the 5 primitive roots of unities for your generator 1 in CMOD 5. Right? Very easy. And the inequality from above would be, well, the sum of the squares of the one dimension of the simple modules, all of dimension 1, so 1 squared plus 1 squared plus 1 squared plus 1 plus whatever, equals 5, equals the dimension or the rank of the group, which is of course 5. So it's semi-simple. Right? So it's a very easy example. 1 squared plus 1 squared plus 1 squared plus 1 squared. And this generalizes for basically all abelian groups, as long as you have the corresponding groups of unities. In the other example, well, you can check that there's actually only one simple module, which is, because you only have one primitive root of unity to play around with, it's a monoidal unit, and the equality is really, really off by a lot. It's 1 on one side, the square of the simple modules. You only have 1, it's of dimension 1. It's certainly lower or equal than 5, the dimension of the group ring. So this is where the formula basically comes from and holds for really absolutely any group, and absolutely any finite dimensional. Okay, that's already not too bad. So let's discuss another example. Also a pretty beautiful one. So here was upstairs basically this example. So this example here is basically the abelian case. And what I'm now going to do is, as you already probably guessed, because I wrote abelian, is additive case. So additive was with a focus on the indecomposables. And all simples are indecomposable. So you certainly have this equality. Let's say again for a finite group. So G is still my finite group. So all simple modules are indecomposable. Not all indecomposable modules are simple, and you kind of wonder how far this equality is off from being true. Again, it's an equality if and only if we are semi-simple. Okay. And the problem is, in the non-semi-simple case, the difference can get basically arbitrarily big. So let me discuss an example. The easiest non-trivial one. And it's really not hard. It's now my group is just a Klein 4 group. This is just Z mod 2 cross Z mod 2. So the group is of order 4, okay? That's not so bad. We can do that. That's what you think, right? That's what you would think, right? Okay, and it's very easy. It comes from, so why it's called Klein 4 group? Well, it basically comes from certain actions on a complex plane by the two generators S and T. And S and T is just S squared T squared equals 1. Anyway, it's kind of the symmetries of here you go, of what is it, of a square. Anyway, in anything but characteristic 2, this thing is, it's fine, right? In anything but characteristic 2, your simple modules L1, let me just call them, how should I call them? L plus plus, you will see immediately what I want to say. L plus minus, L minus plus, and L minus minus. And they're just one-dimensional, and they're given by specifying the corresponding sign for the corresponding generator. Right? So S and T, because they square to 1, have to go to either plus or minus 1, and the signs specify where they go. And you have 4 options, you have 4 of them. And yes, you get again 1 squared 4 times is, of course, equal to 4. So semi-simple. Okay, in everything except characteristic 2, you're fine. In characteristic 2, well, in characteristic 2, you have the problem that minus 1 equals 1, of course. So you can't play this trick anymore, so this doesn't work. And, well, let's see whether I can write down simple modules. And what you realize is in characteristic 2, actually, the group ring is isomorphic to this algebra in 2 generators, and you kill squares. Okay, so it's isomorphic to xy modulo x squared y squared. That's easy to see. Here's the map, but you can also write down a basis here. I mean, you have a basis given by scalars. Certainly x survives, certainly y survives, and xy survives. And this is exactly your 4 elements on the other side. Just linear combinations of them. And it turns out, I mean, it's not hard because you have those elements, x squared, y squared, and how could they act on simple modules? They have to act as 0 on simple modules. And basically, you only have one simple module, and it's of dimension 1. And I don't draw any arrows here. This just means x and y act as 0. Okay, x and y act as 0, and you can see that this just means that s and t act as 1. That's trivial. There's also it's projective cover, and it's this thing. So let's get used to the notation. It is stuff of dimension 4. So I draw 4 vertices. 1, 2, 3, 4. And I illustrate the action of x and y by edges. So x is this action, kills everything else. So x would kill, but for example, this vertex and this vertex. But it sends this one to this one and this one to this one. Y is this action. And that's a projective module in general. As you can see, y squared is 0, for example. Why? Well, because y kills this guy. So if you start here, send it here, and then do it again, it's 0, for example. This is the notation here. And it's not hard to see that this is a projective indecomposable module, and that's it. It's a projective cover of 1, and here is the simple module 1 sitting in the projective cover. Okay, and that's it. Just projective modules. And that's it. There's one simple module, there's one projective cover. So the equality from above is 1 squared is certainly much smaller than 4. Okay. But let's look at the indecomposables. There are a lot of indecomposables. You don't have to understand all of them, but the only point is, well, let's look at this family. So there are 4 families. I've written them down all in the lecture. There's 3, no, there are 4 families. No, sorry, there's 3 families. I've written them down all in the lecture notes, but just let's look at one of them. So you can easily draw a graph on basically arbitrary vertices, and this is the action of x and y. So x acts by shifting every second one leftwards, and y acts by shifting every second one rightwards. And you can easily check that still x squared equals 0, of course, because you omit every second step, and y squared equals 0, yes, because you omit every second step. And this is an indecomposable module of the Klein group in characteristic 2. Okay? And I haven't specified the number of vertices, so there are already infinitely many. Even if you ignore the other classes, there are already infinitely many of the second class of modules. So if infinitely many indecomposable modules in contrast to one simple module. Okay, so indecomposable are much harder than, or much harder to classify and study than simple modules. There's just so many of them in general. Already for something like the Klein group, you get infinite families. while you only have one simple module in total. So, or summarized, here's a statement. So we have a finite group of order m, okay? And P is the characteristic of my field. So M is the crucial number and P is the characteristic, the other crucial number. Then it's a semi-simple category if and only if P doesn't divide M. Okay, that was Muscular's theorem. Very, very easy criteria. It's semi-simple if and only if P doesn't divide M. Keep in mind, for the client 4 group, P equals 2 was a critical case, and everything else was kind of the same. It's always a tensor category. It's always in 10. That means it has always basically, that's the only thing you need to check here is that it has a finite number of simple modules. This is always the case. Why? Because you always have this inequality that the dimensions of the simples, well, you square them, it makes it even better, is lower than m in this case. So you can only have a finite number of simple modules. And it has pivotal and monoidal structure anyway, so the only thing you need to check would be this equality. So it's always a tensor category. And it's almost never a Fiat category, or, well, no, it's also often a Fiat category, but not always. So for Fiat, you would like to have this thing here, so sorry, these things here to be finite. So you need a finite number of indecomposables. Right? And because there is no such equality, this is much harder. And it happens if and only if basically the P pseudo subgroup of G is cyclic. I will discuss this in an example. And this is kind of a classical theorem due to Hickman. And it's, as I say here in the remark, it's actually effective. You could construct all the indecomposables from the P pseudo subgroup. But let's look at it. Anyway, I encourage you to look at the reference. But for now, the only thing you need to keep in mind is that you're always tensor and you Fiat if and only if something happens. Let's discuss the example. Okay, there are two. So that let's say Z mod 4, okay? Z mod 4, Z versus, well, you could ask why I've taken clients 4 group versus clients 4 group, which is in my notation V4. So this is just Z2 cross Z2, right? Z2 cross Z2. So these are the groups of order 4. You don't have any other group of order 4. And as you can see, the only critical characteristic is P equals 2. The only thing that matters is P equals 2. In all other cases, they are semi-simple and everything's nice and fine anyway. And for P equals 2, what you need to check now is what are the two pseudo subgroups. And here, well, the two pseudo subgroup is this thing itself, and it's obviously cyclic because it is a cyclic group. So in this case, you actually get a finite number of indecomposables. And of course, this case is not much different from the one I did last time. So you get those Jordan blocks. And the biggest one you see is of order 4. And in this case, the P pseudo subgroup is also the same, the group itself, which is obviously not cyclic. Not, right? Okay, it doesn't fit anymore, but you know what I want to say. It's obviously not cyclic. And as we have seen, yeah, it has infinitely many indecomposables, as listed here. Okay, and basically that's what you can always do. You look at those cyclic subgroups, the P pseudo subgroups, and you check whether you look at the cyclic subgroup. You look at the P pseudo subgroups and you check whether they are cyclic or not. And if they are cyclic, you are happy. You have finitely many indecomposables, you're Fiat. If they are not cyclic, then you're not Fiat. You have infinitely many indecomposables. Again, in contrast to you always have only finitely many samples. And let's just beef this up a little bit. So I discussed finite groups up to this point, but there's not really a reason to just discuss finite groups. You can talk about more general algebras, or to be precise, more general finite dimensional hopeful algebras. Because in this case, FD mod is basically has the same properties. So you always have a finite number of simples because of this inequality. I just write it like this. So dim. Whoop. You always, and there is a criterion. It's called finite representation type, and it's basically saying that the number of inequalities is finite. So finite dimension Hopf algebra, the category of finite dimension modules is always tensor, and it's Fiat if and only if you're a finite representation type. Just because, again, additive is much harder than a billion. A billion is just rare. Right? In a billion, you focus on a much smaller and much more handleable class of elements. Additive categories, if we care about the additive structure, is usually harder to handle. They are more common, right? We have seen this last time. Brouwer algebra, Brouwer categories, and so on. So diagram categories in general are usually only a billion. Are usually never a billion. Anyway, so this is kind of the thing I wanted to say about those things. Let me summarize. Basically, what I discussed is what is the difference between simple and indecomposable. In a few examples, like the client 4 group, where you have infinitely many indecomposables, and you always define many simples, basically by this really beautiful inequality that the dimension squares is always smaller than the dimension of the algebra. But let's look at something different. Let's look at matrices, because we all like matrices. I hope you like matrices. The best numerical invariant, or arguably the most important numerical invariant associated to some category that we are looking at, are matrices. And this works as follows. So I explained to you how a matrix corresponds to a graph, and you will see a lot of graphs in a second. But basically what you write down are the fusion rules. The fusion rules is the following idea, or the fusion coefficients is the following idea. So if you tensor two indecomposables together, you get an element of your category again, of course, and you can decompose this element into indecomposables. So the fusion coefficients are those n's. It just turns up in those decompositions. So it basically is a structure constant of the Grothendieck ring. Right? That's what it is. The structure constants of the Grothendieck group. And you can write these down in terms of these fusion matrices, which are graphs. So matrices with non-negative entries. Don't worry, we'll see a lot of examples of this in a second. Right, so the associated notion is a fusion graph, which we will see now in a second. Yes. So what you do is, on the Grothendieck ring, you can write down an action by tensoring with a simple module. So you write down in each row and each column, basically the indecomposables form a basis, right? So you write them down in the column and the rows, and the matrix captures the tensor action of let's say one of the indecomposables. So let's say you are in this row, the ith row, then you would take zi tensor zj, you get some decomposition, and the decomposition is exactly what you would write down in the corresponding row, just ordered by decomposing them and writing down the numbers into the corresponding entry. So in other words, you just capture the right action of CZ of the indecomposable ZJ. So we can associate a graph to it. And that's just a fusion graph, and it's very easy to define if you keep it's just a graph for this matrix. Just write down. So by the way, for me now, I think whenever I'm in some Fiat or tensor setup, I will have n indecomposables or n simple modules. Okay. So this is why the set is 1 to n. So basically, what you write down is a graph for this matrix. And those are called the fusion graphs. And you have one of them for each I because you have one of them. Well, I should have written J here because gamma I corresponds to tensoring with Ci. Um, and of course, you can do this for any decomposable for any object actually. That would be just the sum of the corresponding matrices for its decomposable sums. Yes. And here will be an example. The point is that these are invariants, and this is kind of clear by construction, but let me write it down anyway. So the Diffusion graphs are invariants of the category. So let's say you have an equivalent of those categories, and it's of the right type. Right? It's k-linear, additive, rigid, and then up to reordering, the Diffusion graphs of both categories are isomorphic as graphs. Okay. Let us discuss examples. But before we discuss examples, I will discuss an example. That sounds a little bit weird, but I want to discuss the kind of the trivial fusion graph, which is the trivial example. All others will be called non-trivial. So if you think of how those things are defined, so the graph for the monoidal unit, well, what could it be? Well, the monoidal unit just acts boringly on everything, so it fixes everything, right? So Z1 is sent to itself, Z3 is sent to itself, this would be a Z2. Z3 is sent to itself, Z4 is sent to itself. So it's just a diagonal matrix. Right? The identity acts as a diagonal matrix. Okay. I mean, that's a little bit boring, but it should tell you, well, that the story, well, that's what you should expect, right? So what you're trying to do is not completely crazy. Everything else will be called non-trivial. So let's look at more exciting examples. Okay, so here's our example, Z mod 4 again, that we had above. Well, above we had Z mod 5, but Z mod 5 was a little bit too big. So let's take Z mod 4. And as I said, above, Z mod 4 has 4 simple modules. I did it above for Z mod 5, but anyway, it's the same story. And they're given by fixing the corresponding fourth root of unities. So here are the fourth root of unities. 1 I minus 1 minus I. And yeah, well, it's just a multiplication. Okay. And now how does it work? So yes, so they act as the corresponding elements in Z mod 4. And this is now a bit confusing. So I was hesitating a little bit whether there's typo here, but actually there's not. Because as an element of Z mod 4, this is of course 0. This is 1. This is 2. And this is 3. And this is exactly how they act. So this is addition by 1, addition by 2, addition by 3, addition by 0. So the non-trivial ones are this one for L1. It's this thing that sends everything around in a circle. The one for this one sends everything around in a circle in the opposite order. And this one is a little bit fancy because it's addition by 2, and addition by 2 is not an operation that is connected, of course, because, well, 0 plus 2 is 2, plus 2 is 0. So it's this operation, this diagonal operation. Right? 1 plus 2 is 3, and 3 plus 2 is 1. So you have those two non-connected parts. And this is exactly how the fusion graphs look like. And yeah, here's another example for the Klein 4 group. This is how the fusion graphs would look like over C. So again, you have 4 simple modules. They're given by a choice of sign. It's either this one this one, or this one. And you can see that these are really different. So you can see that those categories cannot be isomorphic, because here you have those cyclic graphs, and here you just don't. So there's no way that these things can be isomorphic, which is not a priori completely clear, right? Could be that there's some coincidence, some reordering and some re-enumeration of simple modules or whatever, that this works, but they can't be isomorphic because, well, as you can see, um, well, they're not. The graphs are different. And this is really funny because both cases are semi-simple, so they are actually equivalent as categories, but they're not equivalent in this structure when you add the they're not equivalent when you add the monoidal multiplication, and you can see this from the graphs. So although they are equivalent as categories, they're not equivalent as monoidal categories, which, as I said, is not a priori clear. I mean, in this case, you could check it differently, but in general, those graphs are pretty good invariants of your category. Here's a more fancy example, the symmetric group. It's worthwhile to have a look at it, but maybe it will be a little bit too fast for a lecture. Basically, you have two simple non-trivial modules, and this is a multiplication table. So here you go. And if you know this multiplication table, it's easy to work out. You can write down the diffusion graphs, and this is how they look like. So let me just maybe discuss this once more so that you get used to the notation. So, so here from the matrix, you see you have three vertices. It's 3 by 3 matrix. You have the three modules, the trivial one, then there's a standard one, and there's a sign one. So 1 ls and l1 prime. And the action, as you can see, is of s is it sends 1 to s. This is this column. It sends 1 prime to s. This is this column. And it acts a little bit fancy on s itself. It sends it to here, and you have a loop. This is this column. So it sends it to everywhere. Anyway, so have a look in the example. It's really nice. And of course, as usual, the link to the file is in the description. It's if you understand this example, then you understand the concept of diffusion graphs anyway. So it's not too bad. They're not a complete invariant. That's what this example is saying. But this is kind of clear. But they're just a good invariant. They can't be a complete invariant because they do not involve morphisms in any way. They're basically an invariant ontology group. Okay, I'm starting roughly, so we want to do something. We want to move on. So what we need is a strongly connected graph. This just means a graph that is connected as a directed graph. So this is certainly not strongly connected. This would be strongly connected, as you can see. So I can go from everywhere to everywhere. This is good. This is not good. And a generator or a fusion generator is something for which the graph is strongly connected. Okay. And if you have such a category, you call it transitive. So a category with a fusion generator, with a generator which has at least one strongly connected fusion graph is called transitive. In example, so here, so this is good, this is good, this is not good. So those two are actually good, and this is not good. And here it gets much more complicated, as you can see. Not so easy to see, but none of the simples is a fusion generator. Well, that's clear. This doesn't check. This doesn't check. This doesn't check. But if you take the direct sum of them, you will see that the graph is this form, which is just this graph, and then it checks. So it's not so easy to decide whether something has a fusion generator or not, could be a direct sum, let's say of simple object. And a generator is exactly what you think it is. This was this lemma is saying. So if X is a fusion generator, then any incomposable will turn up as a direct sum of a certain tensor power of X. Right? So it's a generator. You find everything inside of tensor powers of X. In some sense, it's then enough to study those generators. And the way to do this, because they are graphs, is to use some graphs, aka integral matrices, is to use, and this is basically where I want to end. Not quite, but almost. The classical Perron-Frobenius theorem. And it's amazing. It's a workhorse in linear algebra. It's one of the best things you ever see in linear algebra. Sadly, sadly, people don't do it in linear algebra. I think because the proof uses something like the Banach fixed point theorem, which is usually not covered in linear algebra. But the statement itself is a statement of linear algebra. It's a workhorse. It's really of crucial importance in other fields and other parts of mathematics. It's really, really good. It secretly is behind Google's PageRank algorithm, for example. So the way how Google assigns numbers to pages and so lists them in order. Probably the reason how you found this video. So it's really good. So let me discuss it. It's a pretty beautiful theorem. And don't worry too much about this statement. We will worry a little bit about a slightly different version of it, namely the one for graphs. So so this is the classical one. Let's fix a matrix and this is a point with entries positive or non-negative, to be precise, non-negative. So from R So basically from R greater or equal to 0. Okay. Non-negative. Then funny things happen. Namely, basically two statements. There's an eigenvalue, and this is called the PF eigenvalue, Perron-Frobenius, which is, it's also non-negative. This is great. There's a non-negative eigenvalue. A priori, eigenvalues could be complex numbers, but there is actually a real number which is non-negative and which is bigger than everything else. Okay, so you should think of here are the eigenvalues of your matrix, whatever. They're kind of somewhere in C, and then there's a PF eigenvalue, which lies on R. So here's R, and it's just much bigger or bigger than in general than everything else. So this was a really bad eigenvalue. This was also a really bad eigenvalue. And there's somewhere this eigenvalue out there which is bigger than everything else. So this is good. And it's even better. This eigenvalue has an eigenvector, the PF eigenvector, which is also completely positive. So we will see an example in a second. So you have a positive eigenvalue, which is bigger than everything else, and you have a positive eigenvector. And actually, if you restrict to really positive things, then they're basically unique, and equalities are strict. You will see an example in a second, but basically what you think is, as I said, you have this reasonably random distribution of eigenvalues, and there's a crucial one, the PF one, which just stands out. It's just bigger than everything else, like very far away, and it's not just real and positive and bigger than everything else. It also has a positive eigenvector. So you have a PF eigenvector and you have PF eigenvalue. And these are crucial invariants of your matrix. They're just, eigenvalues and eigenvectors are important anyway. And now you have some preferred choice of eigenvector and eigenvalue. And they have to be useful, right? They just have to be, and they are. I sketched a proof. It's not so bad. So you basically prove existence using something like the Brouwer fixed point theorem. So not the Banach fixed point theorem, as I said before, it's the Brouwer fixed point theorem. Anyway, and then you check other things like positivity, semi-simplicity, uniqueness, inequality. It's not so bad. So I can do it on basically 3/4 of a page. It's not so bad. Doesn't matter so much. Read it if you want. It's linear algebra. Up to the Brouwer fixed point theorem, it's linear algebra. And yeah, that's basically it. Well, before we move to examples, let me just say you don't really need the Brouwer fixed point theorem. You can give a constructive proof if you work over the rational numbers. Anyway, usually all proofs are beyond what you would learn in linear algebra, and that's the reason why you usually don't see this beautiful theorem in linear algebra. I say it again because it's important. The proof isn't so important. Well, let's ignore the proof. I say it again because it's important. So any matrix with positive entries has a distinguished, unique, in a very good sense, eigenvalue, which is just far off, right? It's far off. It's positive, it's unique, it's distinguished, it's bigger than everything else, and it also has a positive eigenvector. So there's a distinguished eigenvalue and a distinguished eigenvector, and they're called the Perron-Frobenius eigenvalue and eigenvector. Yeah, and here I give you some examples. For example, if this would be your matrix, then you could check that here's your eigenvalue and here's your eigenvector, and as you can see, both of them are positive. You have to be careful with positive versus non-negative. So if you have 0, something like this, then this would be the eigenvalue and this would be the eigenvector. I will discuss more examples. So this example is basically saying just be careful with the distinction between strictly positive and positive. So 0 is a positive number in this notion. Whatever. I should write non-negative. Anyway. But for graphs, the statement is actually better. So remember that graphs are those matrices, and they could have potentially 0 somewhere, but all other entries are integers. And for graphs, and I give you zillions of examples for graphs, so don't worry, just stay with me. There is something better. So if it's strongly connected, so oriented, then actually PF is not just positive, but it's also bigger or equal to 1. It has a non-negative, so no 0 entries, nothing like this. It has a non-negative, strictly positive PF eigenvector, so eigenvalue, eigenvalue and eigenvector. Eigenvalue is bigger than 1, eigenvector is strictly positive, and whenever you PF eigenvector, eigenvalue, likes to be not so as I said, the standard picture is that you have just, well, this is what I should learn how to draw my eigenvectors, eigenvalues. The standard picture would be that you have some eigenvalues here and PF is just much bigger. This is just what almost always happens, but it could be that PF ends on a circle around things of the same absolute value. But this is basically what the only thing that could happen. So the PF eigenvalue has a certain, potentially certain eigenvalues around the circle of it, but it's still the only positive one. And the corresponding eigenvector is positive. And here's an example. So the proof is not super exciting. Anyway, it's written in the lecture notes if you want to have a look. So here's an example. So this graph. Okay, so for this graph, case 1, you can easily write down you could write it down if you want explicitly. There is the PF eigenvector. It's this one. And something I forgot to say. The only eigenvector with only positive entries, the PF eigenvector, is the one for the PF eigenvalue. So both of them are unique in a certain way. So the eigenvalue is 1. And all other things, as you can see, those things are not positive anymore. Here, the other eigenvectors, they are not positive, and there's no way to make them positive. And also the other eigenvalues are not positive. So this is this case. And it's very easy to see what it is. So here's one. These are, of course, the third order affinities. They're all of the same size, but one of them is distinguished, and that's the PF1. And it has the PF eigenvector, this one here. Okay, for the other graph, we can do the same thing. And I mean, this is amazing. You see an eigenvalue 2, and it has a positive eigenvector. I mean, this is just, why should this be true? This is just amazing. And all the others are certainly not positive. And as you can see, all the other eigenvectors are also not positive. Okay, and this is really a numerical invariant, right? I mean, the only thing you write down is you write down a matrix and you calculate its eigenvectors and eigenvalues. You realize, oh, there's a big one. You pick up this big one, the leading one, let's call it the leading one, the PF eigenvalue and the PF eigenvector, and they're invariants of the matrix because they're eigenvalues and eigenvectors. So what you can do now is you can just define another invariant of your categories, which is called the PF dimension. Of course, it's just Baron Frobenius dimension, and it's just for each object, it's just exactly the eigenvalue of the action matrix, so the eigenvalue of the corresponding graph. And for C itself, it's mimicking this dimension of simple modules squared, just that you now take the PF dimensions of the inequal objects. Let me give you an example. So here's a very nice example. So let's discuss this. Yeah, so here's the lemma, and the lemma basically says, before I can discuss the example, the lemma basically says that things are very nice. I won't go into the proof. I mean, it's not so hard. It's playing with the right well, it's linear algebra. It's playing with the right notions in linear algebra. But it's basically saying is, yeah, PF dimensions behave nicely. PF dimensions are, for invertible objects, are 1. Remember that PF is always at least 1. So the invertible objects are basically exactly those where it is 1. It behaves nicely with respect to duality, and there is an analog of the regular representation, which is kind of the total object, and the regular object, and there's a total object. The total object is just the sum of all of them, and it's transitive if and only if the total object is. And the regular object plays the role of the regular representation. Not so important, don't worry too much. You can read it carefully if you want. The lemma is basically saying PF dimension is a cool thing to consider. It has some really nice properties. But let's discuss this example. So there exists actually a semi-simple category, which we haven't constructed yet. I will construct it later, but let me believe me that it exists, and it's called the Fibonacci category, for a reason that you will see in a second. And it's very simple. It has just two simple. A semi-simple has only 2 simple objects, and well, we have 2 simple objects, and you would write down one of them is a monoidal unit. So the only additional information you need in order to have all the multiplication tables that you need is I would need to tell you what the other simple object that I denote by L, what its square is. And L squared is just the trivial object plus L. Okay, in other words, its graph looks like this. Okay, why? Well, how does L act on the trivial object? Well, it sends it, this is this line, it sends it to L, of course. 1 times L is L, by definition of the monoidal unit. And I just told you how it acts on itself. This is this one, right? So this is the fusion graph, and well, this is the graph. This is the matrix that actually realizes the Fibonacci recursion, the Fibonacci numbers. In particular, if you calculate the PF dimension of L, which is just the leading eigenvalue, so PF eigenvalue of this guy, then you will realize that it is the golden ratio. Okay, so dimension of this object is a golden ratio. Be careful. Dimensions in this setup are positive real numbers, and they could be basically any positive real number. In particular, the golden ratio is a perfectly fine value as a dimension. And yeah, the PF eigenvector, well, it's strictly positive. It has 1 and the up to scalars 1 and the Fibonacci, the golden ratio. And what is the Perron-Frobenius dimension of the whole category? Well, it's a sum of the squares of the Perron-Frobenius dimensions. So it's 1 plus phi squared, because of course the PF dimension of, I haven't told you, but the PF dimension of the unit is of course 1. The unit matrix has 1 as its leading eigenvalue. It has only eigenvalues 1 anyway. So the PF dimension is, well, 1 plus phi squared, and if you factor that out, then you get this one. So again, dimension in this setup is basically some positive real number, and it could be anything. Anyway, so the idea is pretty simple. You just write down those graphs, you compute the eigenvectors of those graphs, and the eigenvalues of those graphs, and those are your dimensions. Okay? So it's just computing eigenvectors. And I just told you that basically any real number can turn up. That's not quite true. It's a slightly better statement. So the dimensions can be kind of algebraic integers, so the roots of some integer valued polynomial, like the golden ratio. So certainly not all. So you will never see pi, for instance. Certainly only some nice numbers will turn algebraic integers. The proof isn't very hard and isn't also very exciting. Here I have a bigger example, which I would like you to read very carefully because it's very illustrative. Let me just go through the main details. So it's about the symmetric group in 3 letters over the different fields. So first is k equals c. Second case is characteristic 3, and it gets a little bit out of hand, as you can see. But don't worry, I will explain. Third case is characteristic 2. And if you think about it, so here's the second case. If you think about it, these are exactly the interesting cases because the order is 6, which is 2 times 3. So the first thing you would check is for everything except characteristic 2 and characteristic 3. So let's do complex numbers. That's everything except characteristic 2 and characteristic 3 anyway, in some sense. And then you would need to discuss characteristic 2, and you would need to discuss characteristic 3. Okay. In this case, you can write down the total object is just a sum of all simples, and it has this fusion graph, this one. Looks a bit scary, but it certainly is strongly connected. So this works. So this is a totally fine generator. The regular object is just this one. So it's just isomorphic to the group rank itself, and you do exactly what I told you above. You take every simple object and you take it's corresponding to the number of its dimension. So this is of dimension 2. That's why you take it twice. Dimension 2, this is of dimension 1. This is of dimension 1. And the equality you should look for is 1 squared plus 2 squared plus 1 squared equals 6. Right? And in this funny case, actually the Perron-Frobenius dimensions, you can check it. So the graphs were above in this example, and this is the one of those graphs, this is the other graph, and you can check actually that the PF dimensions of those guys are exactly, well, this has dimension 1 anyway, exactly the dimensions of the corresponding representations. But that's not a coincidence, by the way. But anyway, in this case, you get exactly our beloved equality 1 squared plus 2 squared plus 1 squared equals 6. It's exactly what we want. In characteristics 3, things get a little bit more complicated. And basically what I do here is, in all of this long part, I basically try to write down the indecomposables. Okay. And it turns out that this is the table. So up to this point. And it turns out that this is a relevant table. I explain above how I get this table. So you have 5 indecomposable objects. Sorry, 6, of course, because in this table I'm omitting the trivial object. So there are 6 indecomposable objects, and I denote them by z1, z1 prime, z2, z2 prime, z3, z3 prime. And the dimension of them is exactly zi is of dimension I, and you just have 2 of them. And I also explain how they are built in this slides. Again, I want you to look at this example carefully. It's probably too fast for a lecture. Don't worry too much. So there is some algebra going on, and there's some algebra here. Oops, this was really bad. This little bit of algebra here gives you this multiplication table. And as soon as you know the multiplication table, you can work out the action matrices and the corresponding eigenvalues and the corresponding eigenvectors. Let me discuss this. So as I said, I have 1 and 1 prime, and 1 is just the identity matrix, and 1 prime is kind of the converse identity matrix. And for those matrices, it's easy to see that PF eigenvalue is 1, and the PF eigenvector is just 1, 1, 1. Okay. And yeah. And what I haven't told you, now I remember that I forgot, and I actually wanted to say that, is the regular object actually is the corresponding Perron-Frobenius eigenvector. It's a vertical object. It doesn't need to make sense because it's a linear combination of potential, a linear combination involving potentially not integers, but it kind of still makes sense in some scalar extension. And you can calculate this Perron as a regular object. You can get it from the Perron-Frobenius eigenvector of a generator of the total object, basically. So you can calculate the PF dimension by just looking at the PF dimension of this regular object. Anyway, it was just digressing. Anyway, so here you have those 2 indecomposables. That's how they look like, or that's how you should think about them. These are the fusion matrices, and just one of them is identity, the other one is whatever, the anti-diagonal identity, and they are both PF dimension 1. So you get here already a 1, and here you get a 1. I've calculated all the others as well. And again, it's no coincidence that they're exactly of the right dimension. So I told you it was also of dimension 3. And those guys here are of dimension 2. Ah, come on. Those guys here are of dimension 2. And yes, if you calculate the corresponding PF, then you get exactly what you think you get. But none of them are actually fusion generators. And of those things are invertible. But anyway, so the PF dimension would be now, I probably do it anyway, I can do it for you, is 1 squared times 2 plus 2, so 2 because you always have the prime version, 2 times 2 squared plus 2 times 3 squared. And it's just different from the one before, right? It's bigger. So those are not isomorphic as monodal categories. So they have different dimensions. Oh, 28 actually. That's what I say it is. Okay. Down here I compute the dimension and apparently it's 28. So if you would do no, what is it? 2 plus 8 plus 18. Yay, it's 28. So as I said below, as I say below, it's actually 28. And yes, so here I've written down the characteristic 2, the multiplication table, and it's a very, as I said, you should really do this yourself. It's a really nice exercise to compute the corresponding PF dimensions. Everything you need is in this table, so all you need. Well, maybe not all you need for everything, but all you need for this exercise at least. And I'm also doing an example with S3, but now as a category G-gated vector spaces, you can have a look at it. You write down the matrices, you get Perron-Frobenius eigenvectors and eigenvalues, and you can check that the PF dimension is 3. Anyway, let me cut off here. I will start with the second lecture from 8.3 onwards. Second part of the lecture. Let me just summarize what we have seen. So what we have seen is I basically tried to write down numerical. So in the last part, I basically tried to write down numerical invariants for those categories we're interested in. And not quite obvious, but what you would like to do is, or what you do is, you write down those graphs associated to objects, and they're just given by basically calculating the multiplication table. And then you fill in the graphs, and each graph has, by Perron-Frobenius theory, a leading eigenvector. Okay, maybe it was a bit too quick, but only thing you need to remember is that there is a leading eigenvector and a leading eigenvalue and a leading eigenvector in this theory of graphs. And that's by definition a numerical invariant that you call the Perron-Frobenius dimension of the corresponding object. And the Perron-Frobenius dimension of the category is just mimicking PF dimension. The classical one I showed you before by just taking the squares of them, you sum, and that's a PF dimension of the category itself. And that's an invariant of the category. It's a numerical datum you want to assign to a category to check. And it's like any numerical datum. If you have a numerical datum of manifolds, whatever it is, a Betti number or homology group, it's usually not a complete invariant, but you kind of split your classification into slices corresponding to those invariants. And even if this, as I said again, even if this was a bit quick, I totally understand. You probably want to do this. If you understand this exercise, you're good anyway. Then you have understood everything I said in this lecture, basically. If this was a bit too quick, yeah, numerical invariants are sometimes. This is one of the easiest numerical invariants you can think of. Basically, you only write down a graph and you calculate its eigenvectors and eigenvalues. And with that, I mean this correspondence from graphs to matrices. So all you need to take away is graphs and matrices are the same, and these have nice eigenvectors and nice eigenvalues, those Perron-Frobenius eigenvectors and eigenvalues, which kind of dominate everything, and they give you a way to define a dimension. Anyway, I'm already starting waffling, so I should cut it here, and then there will be another lecture for the rest of part A. Hope to see you next time.